Hi guys. Hi everyone.
Hello.
Yep.
Hey.
We will start probably the usual 5-10 minutes late because it's the first class. I'll wait a few more minutes. We had about 21 or 22 people registered for the class. Also, just based on my recent experience with online teaching and virtual meetings, if your conditions allow you to use your camera, please use it because it kind of gets everyone a little bit of a better feeling of what's going on, especially, when if I go too quick, too fast, too slow, it's much easier for me to guess this by just looking at you. So there's no restriction, there's no requirement, but if you can enable your camera and it works fine, then just do it. So we will start in around 1:10 Eastern time.
Hello, everyone.
Hi, Mustafa. I see Jimmy here. Hi, Jimmy. I see Yo-Yo. Hi. Yeah. This is going to be a little bit of a smaller class, so I guess it's acceptable. Yeah, have more people. While we're waiting, anyone wants to ask any questions? Like anything generic? Like I will cover all the course logistics and everything. No worries, that will be covered on the slide deck.
Like, will we be having some in-person components this semester, or is it going to be pretty much online?
Yeah, so originally I was planning to have some in-person component for this class. The problem is the rules and regulations, essentially at the university, we cannot read, like say we reserve a room and I bring everyone in the room. So the problem is if someone doesn't want to wear a mask, I have no way to tell, and someone else is uncomfortable with it, I have no way to resolve this problem, right? So it's like I have no power. I can only recommend things, right? University has no, like they have rules, but they had no enforcement in it, right? So until university figure out what to do with it, it's not like I have any specific problem with someone wearing or not wearing a mask. The problem is if someone else is uncomfortable, right, wearing or not wearing a mask, I can't really do anything about it, right? And in some cases, if someone says, no, can't have a lecture like that, so what should I do? Stop a lecture and like not having it? So there were multiple times the department got these questions. They have no answer to that right now. So until they figure it out, we can't really have a proper in-person component. All that said, I'm not completely hopeless. At least some things like poster session or something we might have in person. Like this class is research oriented. At the end of the day, we're going to have presentations and posters, right? I can clearly see how the poster session can be actually organized in the whole of something like Bain, right? I guess in Yao is like remote, right? So we'll have to figure that out, right, for you. We'll put like a screen with your poster or something. But for everyone else, that might be a possibility, right? Yeah. Okay. Any other generic questions? Okay, let's wait a few more minutes. By the way, before I was like, can you guys hear me well and can see me well? So everything is fine? Okay, good.
Yep.
So that you know, like I automatically, like all these meetings are automatically recorded whenever I join, right? So that you know. So if you're working for some company in parallel to taking studies, making sure they don't say anything confidential here. Yeah, so, and those videos will be posted otherwise. This is not to discourage people to attend the meetings, but it's more like for your own convenience, right? And slides will be shared. They already actually shared for today's lecture. Sometimes I'll try to share them, a few hours before the actual meeting, right? If I don't share them, and you really want to see what's going to be in the lecture, I taught this class 3 times before, so you can go to my webpage, go to the previous year class, and roughly see the slide decks from previous years, right? So things like DRAMs and GPUs don't change as rapidly, so most of the content will be similar. Yeah. Usually in a small class like that, by the end of the semester, I pretty much learn like the names and visual appearance of most students. So even students that don't have cameras today, in the future, if you sometimes can enable your camera, like not today, but in some future times, that would help me. So I associate your name with, image. So that helps. Yeah. Yeah. Yeah, in terms of how to ask questions, in large classes, I usually ask people to ask everything in chat. Yeah, Mustafa, no problem, that's fine. So again, this is relative to you unmute yourself and ask your questions. I think it's okay. Like if it's not rush, you can just put your question in the chat. But if it's something related to the current slide I'm presenting and something isn't clear, you want some more details, actually it's okay to talk, right? It's not 100 or 200 people class, so you can actually talk, right? So unmute yourself, ask your question, that's totally fine, okay? Okay, we will start in about 30 seconds. Okay, so let's start. So first of all, I'm Gennady Pichimenko. I will be your instructor in this class. I welcome everyone in the first virtual edition of this class called Parallel Computer Architecture and Programming. So this is advanced graduate level class. Most students here are graduate students. I guess there are 1 or 2 exceptions, but most students are graduate students. So this is very open-ended class where the main focus is on you doing an interesting research. So it's supposed to be very interactive. Most of my colleagues actually do those seminar-like classes where students just present every lecture. I felt like we're going to do that as well. You're going to present, but more towards the end of this class. So essentially, at the beginning, I'm going to use some of my time to kind of present to you some of the most recent and interesting stuff so you can build up some background on computer architecture before you will start to present on your own, right? And I'll cover things related to architecture, but not only. I will talk about the general research. Like I know some of the students are not necessarily in this area, but they might be in systems, in graphics, in all these other different areas. So I'll try to talk on things that are relevant to your research areas as well, okay? So, okay. So let me go to the next slide. So what we're going to cover today. So obviously we need to cover all the logistics, grading, course introduction. So I will do this up front. So we don't need to go back to that again. So usually I would have a physical information sheet, although this is less needed right now, so probably not going to do that. I'm going to talk about paper reviews and presentations, which is a big part of this class, and how to handle those. So I'm going to talk about what me and your TA would expect here. I'm going to talk about project, which is the major part of this class, not about the grade, which matters for some of you, but should be less matters when you're joining the grad school, but more about how you can actually deliver something interesting in 3 months and what you should do for this to happen. And then I will talk about some technical stuff a little bit. So I expect, usually we had 3 hours reserved. I never use 3 hours. We use 2 hours at most. And then the third hour, if you have some questions, especially at the beginning, there are less questions, but more deeper in the semester, some of you will start with come with questions about your project. So we will use that third hour to, answer your questions or advise you on what you should do with your project, right? So but roughly you should expect 2 hours. We'll start 10 minutes late so that everyone can join. Then we're going to have roughly in the middle, we're going to have a break. So it might be not exactly at 2, but around 2, right? We're going to have a 10-minute break and then we continue, okay? So that's just on logistical. The lectures will work. So the first questions, of course, who are we? Who are the people who are going to teach you? I'll start with myself. So I'm Gennady Pichimenko. Don't try to pronounce my last name correctly. That would be difficult. So you can either use Gennady or Gena, my short name. That's good enough. So no formalities needed. So please avoid terms like professor or something. Just by the first name is good enough. Okay. So I'm an assistant professor here in computer science department. I also have a courtesy appointment in computer engineering department. I'm also a faculty member at Vector Institute, right? I'm a member of the systems and networking group, like all systems people in the CS department. I also run my own group called EcoSystem, that stands for Efficient Computing Systems. So this is my email, this is my web page. My normal office is in Bain, although I haven't been there for quite a few months right now. Even though the university is open for faculty, there's not really anything to do there when there are no my grad students there. So I really not particularly excited to come back until the lab students come in, which is started to happen. So they allow a limited attendance by the students starting, I guess, this week. So you can spend at least a day per week right now if you sign up for a certain schedule. Okay, back to myself. So I got my PhD from Carnegie Mellon University. I got my master's actually here at the University of Toronto. I got my undergrad degree back in Russia in Moscow State University. I worked in quite a few companies. I work at Microsoft Research. Most recently, I work at NVIDIA. I work at IBM. I also had smaller stances at companies like Intel, and I will be working part-time soon at Amazon. My research interests are in computer architecture, systems, machine learning, compilers, hardware accelerations, and a little bit of bioinformatics. So I had quite a wide area of research interests, so that hopefully fits with something that you would do. Okay, so your TA would be Hussein. So he's a PhD student in computer engineering department. You would probably notice that the course I'm teaching here is of interest to both CS and EC students. So there are going to be a substantial number of students from computer engineering department here. So Hussein took my class, I believe, 2 years ago. So his research interest in computer architecture and interconnects. So I think he's in Natalie and Rai Jerger's group there. So he will be the guy who will be, grading your paper reviews. Okay, so course information. So there are 2 main places to get information about the course. One is the course website, right? Here's the link there. So slides will be shared, already shared, right? So that's where we're going to post some announcements, although we prefer to use Piazza for that. Syllabus, course information, lecture notes, videos, everything will be posted there. The grading schemes, all this information that you need to check on all the deadlines, it's always there. Piazza is the place to keep the discussions going, to ask questions, and the most important part, to search for teammates. So you're going to do a project in this course. So you would normally can find the teammates in the room, but now you're all remote. So you would need Piazza or something to start this remote conversation with someone else about the projects, right? Because you are supposed to do the projects in teams. So here's the links for Piazza. I pre-registered you. If your email mismatched with what I got from the department, then please just go by this link and register yourself on Piazza. So very occasionally I might use your email, but I prefer not to spam students. So like most of the communication will be through Piazza, and everything that is static type of content will be on the website. Any questions so far about the logistics? Okay, 1, 2, 3. Okay, let's move on. So those are the major logistics that we covered. So I hope now we can talk a little bit about more interesting content. So I'm gonna teach you a course on computer architecture. So what does this really mean? So here is more or less the definition with what computer architects, people that work on computer architecture, agree on. This is the science and art, both of that, of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system. So you see there's an important pieces there. It's both a science and art, right? And it both design components and design things out of components. And the goal is to build a computing system. So we do build real artifacts at the end, either prototype or really tape out, but the goal is to make something working. This is in contrast to some theoretical courses where everything doesn't really build anything necessarily. And we care about functional, correctness of these things we build, its performance, energy and power consumptions, and cost, and any other specific metrics that people in reality have. So it's science and art, but it has the metric and it has real components. So the main goal of architecture is to build something interesting from the hardware. There is also a traditional definition that I leave you here that goes back to the Genome Dals in April 1964, and you can see how things change since then. Yeah. Okay, so how should we look at the problems in this course? So they're usually the way we start with the problem, right? We don't normally having a solution and we're running to find application of the solution. We start the way I do research and the way most computer architects operate is we look at the problem that exists. And then we had the very deep stack, computing stack that allow us to solve problems. So at the bottom, there are circuits. At the top, there are applications. Under the application, there is usually some form of the operating system, right? And in between, there's an architecture. So this is the level where the computer architecture is located. It's roughly in between the circuits and the operating system. And this interface between software and hardware, this is what we do. So sometimes people confuse there. Some people think that architecture is more of a system stuff. Some people think it's more of a circuit stuff. It's neither. It's really the interface between software and hardware. Its unique role allows you to be an expert in both fields and try to drive the information and knowledge between the both areas. A lot of things we had to deal in systems and architecture goes back to one of this key concept of abstraction, and it's a very powerful concept. So the abstraction consists of two parts. One is an isolation, so a higher level of your stack only needs to know about the interface to the low level. They don't need necessarily to know how is it implemented. So whenever we're going to talk about DRAM, they're going to be point in lecture where we're going to look deeper into DRAM, but they're going to be points where we just need an API from DRAM. I know I send a memory request and the data arrives back. So this is the beauty of isolation. When I don't need to know how a component operates, I can abstract out its functional implementations. I don't really care how Micron versus Hynix versus Samsung did this DRAM model. As soon as it follows certain API, right? That's the power of isolation. For example, high-level language programming doesn't really need to know about the architecture that much. If you're using Python and really don't care about performance as much, you barely need to know how the architecture operates. Although I really hope you guys know, other languages other than Python, so you can actually care about performance. So productivity-wise, so abstractions allows you to not to always worry about decision made under low levels. So if you had a, say, cache or DRAM specification, and you meet that specification, right? You don't really care about how they figure it out, right? That's not your problem. Okay, I got a question. Let's see. Okay, I see. Okay, so for example, programming, you can program in Java versus C versus assembly versus binary by specifying control signals of each transistor on every cycle, or even Verilog and things like that. There are all these levels of abstraction that can be, depending on what you want, you can do each of that. That's the productivity component. Okay, so when we deal with abstraction layers, there is this typical questions we ask. Should we always focus on one layer or our own layer? And the typical answer I give is, as long as everything goes well, it's okay to stay within one layer. So it's okay to not knowing what happens in the underlying level, to not become crazy about complexity of the problems, because we're dealing with a very complicated system these days. I don't think there exists a person in the world that would understand all the level to, I don't know, to the bit granularity, how the full system operates, right? Nevertheless, things somehow work, right? So it's not a single human that knows the whole system operates, but I mean, it's still functional. So there are cases where you need to understand what the other things are doing. If one of the layers reaches its limit, either performance, energy, or cost, right? Then there is no way to improve others. We need to have a way to deal with that problem. For example, like one canonical example, for a long time, people don't care about memory as much. So everything was about processor, about the computation. 70s, 80s, 90s was all about processes rather than the memory. Until the delta in performance between compute and storage memory reached the limit where the memory becomes the bottleneck. It first becomes the bottleneck in terms of performance, it's a so-called memory wall, but now it's a problem in terms of cost. If you're actually a cloud provider like your AWS or Azure, you would know that the single most expensive component of your node is not your CPU, it's not your accelerator like GPU, it's actually the memory. So memory can be as expensive as 40% of the total cost of a data center node. So this is where the priorities in research and in R&D and development can shift. Another reason why you want to look across the layers is when there is a new disruptive change in technology that cannot be contained in a layer. So what are the examples of those? Well, for a long time, for maybe like 30, 35 years, the only memory we use for main memory, like there was a DRAM technology, right? For cache, we use SRAM. For main memory, we use DRAM. But then a few years ago, non-volatile memory became practical. So non-volatile memory is not just a new technology to do exactly the same thing. It brings a lot of new artifacts, positive and negative. It brings the feature of non-volatility. It means if I use it as my main memory, I might now have an instantaneous boot. I don't need to start my DRAM from scratch every single time I turn on my PC, right? Actually, everything is permanently stored in this non-volatile memory, so my boot can be like really instantaneous, right? So another example from the NVM as well, that was a positive feature. The negative feature that affects all other layers, that these things is now destructive. So essentially, reads and writes in DRAM, we always thought about them as infinite. I can do as many reads and writes as possible, but everyone who deals with Flash, same thing with NVM, you would learn that there's only a certain number of cycles on read and write after which cell starts to break. It's not always easy to contain the problem of wear out in just at one layer of the memory. So sometimes operating system needs to know that some blocks of your memory are now dysfunctional, right? So this is open up, a lot of possibilities, but also some challenges. Also, new applications that are too slow for today's system might be only optimized across the full stack. And in general, I really like to do research across the full stack. I really don't like to do things in one level, so it's also my personal preference in terms of research. Okay, so what is the scope of this course? So we're going to have a broader view of process and memory design. We're going to cover things related to processor, but I would mostly assume you had experience with basic computer architecture classes here. So I'm going to focus on more advanced features. I'm going to talk a lot about memory, mostly because that's where a lot of my expertise is. And this is because this is one of the most bottleneck part of the computing systems right now. You know, things like branch predictions already, we're talking about 98, 99% accuracy. So that's very difficult to improve those. So we're going to look beyond just ISA microarchitectural levels. We're going to focus higher up in this course. So in that sense, it might be very different from the C versions of this course. I would highly encourage you to apply out-of-the-box thinking in this course, because it's all about research. It's about how you can find either interest in research in this area, or how you can connect computer architecture or parallel programming with your research area. So please think about these new and aggressive things like hardware acceleration, processing in memory. So it's not an impossible thing. Like 10 years ago, say processing in memory, people thought it's a joke, right? Right now, there are actually startups, not just the company, that are building those processing in memory chips. I had collaborators at UBC right now that are actually working with one of the startups in Europe that actually ship this stuff already. Approximate computing system, persistent memory, neuromorphic computing. Again, things, if we would talk 10 years ago, people would think about this more like reasonable science fiction, but still not science. Now all of that exists, right? Everyone heard about Neuralink, persistent memory right now physically exists. You can buy non-volatile memory chips. We actually had one machine in my lab, one of my students doing research on non-volatile memory. And obviously, in order to learn and being able to apply this out-of-the-box thinking, you need to understand what the state of the art is. I can't really teach you all of that. So what I'm going to give you, I'm going to give you a sample of papers on different topics, which you're going to formally review and try to criticize and analyze. But you're encouraged to keep reading way more than that, right? So I'm not going to restrict. I don't want to force you to read, like, 3 papers every week. When I took similar class at CMU, we were supposed to read 3 to 4 papers each week in this course, and that was a very high load, I had to say. So I don't want that, but I want you just to show how to read papers properly, teach you how to be critical about them, and then hopefully that would encourage you to read more papers, right? So don't read that whatever I'm going to show in this class is enough to understand computer architecture properly in terms of research. No, this is just a sample of things you see. And you're going to see papers of very diverse type. They're going to be papers that are classical architecture, more system-ish, more theoretical PL-ish. So they're going to be a lot of different papers, okay? Okay, so what are you going to learn? So you're going to learn a lot about this hardware-software interface, its major components, and programming models of a modern computing platform. So the big part of this course, and that's, I would say probably honestly, is the most challenging part of this course, is there's no shortcut. We're going to work on the state-of-the-art things. So everything we're going to talk about is essentially as good as the humans were able to invent in the last, up to this point, right? So most papers were as advanced as they can be. So very frequently you're going to see that by reading certain papers, you miss a lot of background. Don't be surprised. People spend 50, 60 years of research to reach this point. So sometimes you would need to do some reading of your own. We're going to learn a lot of trade-offs and how to make them. Pretty much everything in computer architecture, it's a trade-off. Usually as an architect, I have a budget of cost, budget of power, budget of area. And then I need to play at tricks within this budget, right? So essentially, it's very important to understand how that works and making sure you do this properly, right? Okay, so you will get some hands-on experience and research in computer architecture topic. It's going to be, you're going to have a semester-long research project, and the focus is on how to design better architectures. So this is by no means an intro course. This is advanced grad level course. So The goal is to broaden your research vision. So as I said, we'll read papers not only from computer architecture, but from other disciplines, from circuits, from programming language, from operating systems, graphics, networking, and some other areas. Okay. Okay. So what are the main course goals? So the main goals is to rethink and redesign our computing model, focusing on minimizing data movement and storage. We want to understand the importance of cross-layer research. We want to gain new insight from VLSI circuits, architecture design, systems, programming languages, and new application domains. There are going to be a strong emphasis in this course on the critical analysis of research papers. So you're going to do this through reading and performing some literature reviews. So as I said, there's going to be some standard papers that we will pick and ask you to review. Then as a part of your course, you will have to prepare some background and literature review assignments so that the papers will be selected by you, not by me, right? And then you're going to present, your analysis of those papers in the second part of the course. Another goal is to provide you the necessary background and experience to advance state-of-the-art in computer architecture by performing cutting-edge research. So how is it different from other courses? As I said, there are many courses in EC and CS department where there's advanced computer architecture class. They all consist of reading alone. What I found then, without some background and sharing of my experience with you, you might not be as efficient in performing this cutting-edge research. So this is why this course is mixed half and half. It consists, the first half consists more of a lecture type of things where you start to learn things. And the second half of it is actually going to be, more focused on what you do. Yeah. Yeah. Okay. So what is required from you in terms of background? So first of all, basic architecture, right? Basic compilers, basic OS. Those are the skills that I more or less assume, right? So if you don't ever take a class on architecture compiling OS, you would have to learn some of the basics on your own, right? So this is not something I can cover in this class. There's just physically no time for that. So you don't need them like everything from those classes, but essentially you would need some stuff. So if you would be coming from UofT, the basic OS class would be something like 369. We had the basic compilers class and the basic architecture class as well, especially in the C department. So this is what is roughly needed. If you're not sure about your background and how much learning is there, talk to me. We'll try to figure out something out. I might give you some advice on what you need to read to be ready to deal with this course. Obviously, you would need programming skills. So remember, we're going to develop things. So we're developing in this area means programming. So you need to have a good hacking skills to do a research project. But more importantly, on top of all of these standard requirements, you need to have spirit, excitement, and dedication to be interested to explore this new topic in computer architecture that you're going to select for your project. Any questions so far, guys? If you don't ask questions, that's going to be a very fast lecture today. So I always expect certain level of engagement. I know it's a little bit harder since we're remote, but please don't be shy and ask questions.
I have a question.
Yes, go ahead, Andrew.
Yeah, so what are some previous examples of past projects, if you have any?
Yeah, so there are some examples of the projects. I can talk to some of my students who took this class. Like, for example, so one of the project was related to computer architecture and deep learning, a very popular topic these days. For example, one project was given, say you have your applications like your machine learning model on that particular machine, you want to know how it's going to run in the cloud GPUs that otherwise not available for you, on any new hardware. Is it possible for you, without buying and paying this huge cost for these experiments, actually predicting the runtime for each particular model? So the goal was, given a model X and hardware Y, can I predict how fast you're going to run on a new hardware, right, without actually having access to this hardware? So this is one project that I guess Pavel is familiar with, because he was working with one of the graduate students on this project. Another student of mine was on the non-volatile memory. So the goal for his project was to explore because for a long time there was a lot of research on non-volatile memory, but everything was on simulators, right? There was no real non-volatile memories. But then about 1.5 to 2 years ago, the real chips arrived. So the first thing was to understand what they really deliver, how to port existing applications to them. So the problem is, I had this fancy new technology with non-volatile memory, but to use it as a memory, not as a storage, I would need to transform my application in using UAPI. So how much extra work it is, how difficult it is to program it, and how to get most of the performance benefit of it without asking too much from the programmers, right? That's another example of the course. So obviously students from the C department has the tendency to do more circuit architecture level things, while people coming with, say, PL background, their research was more coming from their research area. Yeah, my strong advice selecting the project is trying to connect it with your research area. I know some other faculty, when they teach in those classes, they don't allow your research being a part of this course. I'm actually not as strong about that. As soon as you find the good application of your research area to this course, I'm fine with that, because I know if it's going to be related to your research, you're going to, invest way more time and effort on making it to work than if it's just for this class. Okay. I know it was a little bit long answer. I hope it answers your question.
I see, thank you.
Okay, any other questions so far?
I had a question. It's a bit long. So
yeah.
I am a new grad student, like joining University of Toronto, and this is my first semester.
Yes.
So I just saw the profile of this course and enrolled into it. So currently my research area is not that well defined, but I started to think that serverless is one interesting area that I wanted to go into. And I don't have a lot of background into computer architecture. So what would you recommend in this case? Like, should I invest a lot of time and read about this and like experiment something in this course and try to frame a project that connects to serverless? Do you see that as an option?
It's possible, but it's not required. So for example, if you had a certain skill set, right, and you want to apply it, you might find that there will be other people looking for partners, right? So you might just offer your help with if they had a well-defined agenda. Honestly, I don't think there's going to be a lot of time here to build up the computer architecture expertise from scratch. So if you like it, you're going to learn things, but it's going to take time. So you're probably only going to get some of that expertise 2 months from now, but you should start working on the project or building a team like next week, right? So I strongly advise you, so essentially to not work on that and spend all your time on that.
Okay.
Okay.
I have a quick question. So considering that the course is like run remotely, how should we go about like trying to like find a partner? Especially like in my case, like I'm a undergrad and I don't really have like a research like area per se. So I'd most probably be like looking to like help someone else.
Yeah.
So like, how do I like go about like finding, or like, is there some sort of like research?
When I talk about Piazza, yeah, Ibrahim, your case is totally understandable as you're an undergrad. So for undergrad, unless you really have a strong vision what you want to do, I would strongly advise to join one of the grad students, right, on their project. So what's going to happen is that usually it would happen in a room. Right now, there's no room where all sit. So the synchronization point would be Piazza. So a lot of people that don't have partners, right, would look for one. I would explain why this happens, because if you're like a more senior grad student that know what you're doing, the problem is for this course, you need to find a partner. So they know what they're doing, but they still need a partner. So they would start to post, descriptions on what their skill set are and what kind of project they want to work on. And you should do matching through Piazza, right? And again, This is not a 100-person course, so we're talking about not more than 20 people, so you can literally go quickly through those profiles and see what fits your needs, right? To be honest, like, it's probably better to talk to a few before commit to anything, right? You want to see whether you click with this person. Building a team is a special thing beyond the scope of this course. So you should talk and see whether you click with that person and you think that you would be comfortable working with them for the whole semester, because the course project is a big part of this course.
Awesome. Thanks.
Yeah, and in general, like if you lack some background or not sure which project to pick and you hesitate, it happened before, especially as you're an undergrad, just come and talk to me one-on-one. We will figure out something. And if you didn't find a team, we'll figure out something for you, right? So no problem. We'll find you mates. Like, the main thing we need is your desire to learn and contribute, and we'll find an interesting project for you. Like, as a senior undergrad, you're not that much different from, say, a new master's student who just joined and don't have a topic really, right? So you can still learn. It's just there is an advisor that tells you what to do and you don't have an advisor. So I can play this role at the beginning. Okay, make sense?
Okay, thank you.
Okay, thank you guys. And yeah, any more questions? Yeah. So yeah, don't hesitate, interrupt me and ask questions. You're clearly gonna have some. Okay. So let's just go a little bit more through all the formalities. So what do I expect from you? No surprise, similarly to my grad student, I expect you to work hard, ask questions, actually ask a lot of questions. This course is different from undergrad classes where sometimes you get a lot of, very basic annoying questions on where to take slides and things like that. So here I do expect a lot of hard technical questions. This is why I'm here, right? This is actually totally normal. So don't be afraid to ask questions. Think critically. Don't take everything I say for granted. Moreover, don't take anything for granted what are written in the papers. Remember, the papers were written to get accepted. So they try to, promote their strengths and hide their weaknesses. It's always the case. It's no difference in science as, marketing. Participate in discussion actively in the class, critically review the assigned research papers and readings, discuss the critiques with the peers and us. So even though you write your review on your own, it's your own work, it's totally fine to read the paper and go with your peer and talk about, say, you know what, this is completely nonsense. I don't know how they build it. I think this is a strong weakness. And then from these discussions, you can take the point and write them on your own, right? But it's totally fine to discuss it with others, right? Use Piazza, write good reviews, start the research project early and be focused, right, to deliver something. So there were cases in this course, and I'm not exaggerate, where the research from this course becomes a top tier conference papers. Obviously, it doesn't happen with every project, but it happened. And this is ultimately what I'm trying to do. So I'm trying you to do something that would be like a scaled down version of the full research project from the beginning until the end, from the search for the problem to the discovering of the existing limitation of existing system, doing literature survey and going all the way. And ideally, maybe later you'll publish a paper on that. And it did happen with my students. Yeah, and it happened with some other students in similar courses in this department and at CMU. So how I can ask questions outside the time of the class? So the best place to post questions is still Piazza, right? So because we're all busy, so we not always can answer them online. So post the questions there. I will get to them or TA will get to them, right? And if we don't get to them in time for the next class, then just stay after the 2 hours of the lecture and talk to me about the questions you have. Okay. Okay. And remember that even though there are chances, the chances always favors the prepared mind. So the people that discover things by luck, it's really, they're usually very prepared to get the benefit of that luck. Okay, so formalities about the coursework. Okay, one more question. Okay, so project. Most of the project I expect to be groups of 2. It's easier for you to communicate. It's easier to do it logistically. Sometimes if the project is a bit more aggressive, we might allow a group of 3, and especially, if we had an odd number of students, then obviously some groups I would rather have a group of 3 than a group of 1. Let's put it this way, right? A group of 1 is just too much pressure on a single student overall. So your project is going to consist of certain parts. It's going to be similar to how you would normally do research. You do some proposal, you do progress report somewhere in the middle of the project. And the way I'm trying to do all these parts such that everything you do is not wasted. So it's not like you wrote proposal and then you throw away all the writing and then you write the final report at the end. Every piece, proposal, progress report is going to be an integral part of your final presentation and final report, right? So at the beginning of your proposal, you do some like pre-initial literature survey and the study of the problem. That will become your motivation section in your final report, right? So the goal is to show you how the real paper is written, out of which pieces it is built, right? Then you're going to have a final presentation and a final report. Final presentation, but we'll see how it goes. I would still prefer that we have it as a poster presentation, right? And if things go well, fingers crossed, I don't know what's going to be in Ontario in a few months. Nobody knows, I believe, right now. But if it's possible, we'll try to have it in person in some form. So I'll explore this option. So we were probably going to get one of the rooms in Bayern, and we're going to push things outside. I'll try to figure out something so you can get a little bit of in-person experience where people can look at other posters, ask questions, right? It won't be just, virtual. And the final report is going to be a scaled down version of the paper. So it's going to be written as it would be a real paper with all the proper sections: abstract, introduction, motivation sections, your key idea, your mechanism, your methodology, and your results, and some conclusion. It might be not as powerful and fully novel as a state-of-the-art, papers at ISCA and micro conferences, but it should be aiming in this direction. So the goal is to have a scaled-down version of the real research project. And if you're wildly successful, you can just continue this beyond the semester and get a real paper at that, right? So that you would actually feel you achieved something. This is why I really encourage you to actually, make it connected to your research area. Don't make it a random project, right? If you don't really grad students yet, then it's okay. You will join some project or really cannot connect it, it's fine. But the goal is usually do this. We're gonna have, so project is 50% of your grade. In general, most of the grade in this course is towards the end because that's where you're gonna grade it. In general, I hope you're taking this course not because of the grades, right? You're just taking it because you actually want to learn something. So usually the grade is not a huge concern in this course, unless you're really asking for trouble and not gonna do anything. So paper reviews, so 1 to 2 papers per week. I expect we're gonna have more detailed information about that later, but I expect 3 to 4 paragraphs of a certain structured text, about 1 page, maybe sometimes a little bit more, it's up to you. But I don't need a long essay. It's a scientific writing, so it's a very specific. You have one summary paragraph, you talk about the key strengths, you talk about key weaknesses, you talk about how things can improve, and what you learn from this paper, what you like, what you dislike about it, right? This is pretty much what you're supposed to write about it. Sounds easy, it's not as easy. You're gonna see that this is really, interesting papers to read, but not as straightforward. Remember, strengths are usually super visible, weaknesses are usually super well hidden in those papers. So you would need to discover those. Okay, any questions about that? Okay, so then paper presentation. So what you're going to do, so remember there's going to be final presentation, but there's going to be also something called paper or papers presentation. So whenever you define your project, you're going to learn, like you're probably not going to be, it's going to be built on top of something, right? So it's not going to be in the middle of nowhere. So there is some related work in your project area. So that's what you're going to present. You're going to pick 1, 2, 3 papers maximum, and you're going to go in depth in class with your partner. You're going to go and present that to the rest of the class. And we're going to do, ask you some questions to understand better on what was done, maybe provide you some extra information and, criticize your critique. So if you're too critical or not critical enough, we're going to provide you feedback on what you should do. It will be done by me, but remember, it's like I will be grading that part, but others are supposed to participate and actually give you advice. So grades are not the main part of this course. I try to emphasize it super strongly. I know a lot of you coming just under undergrad, still with the mentality that grades is everything. So I don't know how much you talk to your advisors, but things are very different in grad school. So it's all about research. Nobody cares about your GPA anymore. Like everyone cares about what you can contribute to the state of the art. It's a very different mentality. It's about what you built rather than how you were graded. Okay. So class participations is 10%. It's very important. That's why I suggest that try to make sure that I memorize your questions and comments in a positive way for those lectures. So that would be easy for me to grade your participation at the end of this class. Okay. It doesn't mean to be asking questions after every sentence. It really means to ask interesting, insightful questions or giving some comments. Is this clear? Okay, no midterms, no exams, right? This is one of these courses that are not affected by the virtual part too much because everything is about research anyway. Okay, grading, as I said, will be back-end heavy. Most of your grade will be determined late. So how you prepare and manage your time is important. But as I said, I repeat one again, grades should not be the reasons for taking this course. It is heavy loaded, but not because of that it's hard to get a positive grade there. It's just because if you want to get anything useful from this course, you would need to invest time in research, right? But not because of the grades, okay? Okay, so let's talk about paper reviews. I doubt that a lot of you got experience. Like I think some of my students got exposed already to how to do paper reviews because I intentionally teach them. I found that you can really graduate a strong master's or PhD students that doesn't know how to review papers. So I pay a lot of attention to that. So, but if you never learn, I'm trying to give you a little bit of a summary here. So what you should look for is brief summary. That's your intro paragraph. What is this problem that this paper is trying to solve in your own words, not necessarily exactly the words of the paper, the way you understand it? What are the key ideas of the paper? What are the key insights? What did you learn interesting? What is the key contribution to the state of the art at the time it was published? Remember, papers we're going to review are not necessarily published this year or last year. So it's not fair to assess them by saying, oh, they didn't use, you know, the latest, greatest GPUs or TPUs. Well, you know, those things didn't exist back then, right? So try to put yourself to the time where the authors wrote and this paper and did their research. So what are the most important things you take out from this work? So this is a brief summary. The most important strengths, again, not by the way the authors try to sell them, but mostly by your judgment. Does the paper appear to solve the problem well on what was reported? Sometimes there are some papers that propose new ideas or the ideas ended up being not interesting, but they might use some new benchmarks or discover some side, you know, effects of their measurements that becomes a new interesting thing. So sometimes the side effects of the papers has more importance and higher strength than the papers themselves. The more difficult thing, finding weaknesses. Again, remember, you are going to read the papers that were published. In fact, you're going to read the papers that were published in the top tier venues and one of the best published in those venues. So these papers are going to be very well polished of a very high quality. It doesn't mean they're easy to read, but they are very well written. What does it mean? They're going to look like everything is solved in many cases, right? It's because they're written the way to be accepted, right? So the authors try to downplay their weaknesses and highlight their strengths. So that's the hardest part. You need to be critical. You need to read and think on your own. Don't trust what the authors say. You're going to see that even the best papers, getting best paper awards, have a serious weaknesses in them. You're going to see even the papers written by Turing laureate winners going to have a significant weaknesses in them, right? So you're going to see all of that in this course. We're going to have some of those papers. So you're going to see that. Every paper idea has a weakness. So this does not mean that the paper is bad. It just means they were able to solve something, but not everything. This is why we push the science up front. Every single paper I wrote has some weaknesses. It didn't solve everything, right? It's very hard to write the paper that just says problem solved. It's possible, more possible in theory, where you say, you said, well, there was the statement that whether this theorem is, true or not, and someone make a counterexample, the discussions is over, right? So it's not possible. In systems, it's a totally different story. People propose things like virtual memory. Like 50 years ago, people don't believe that the virtual memory is required and they program without it. Then people propose it, take 10 years to convince people to use it. Now all of us use it right now. But you know what? The last 5-6 years, there are several proposals to get rid of virtual memory for many reasons in certain cases. So the fact that something was decided at one point of time doesn't mean that's a good idea moving forward. So sometimes you revise decisions made. There were even people who revised some of the older paper and found that they missed some big things and like the conclusions do change. I myself did some research where essentially the common wisdom was broken, and I was saying something that was impossible is now possible, or something that we considered to be optimal is not optimal anymore. Another question you need to think about is how can you do better, or if you're really aggressive, how do you do much better than the authors? So present your thoughts and ideas. And remember, you not always can just propose something super radical, but try to think about, right? I want to see your thinking, right? That you try. I want to see this effort to propose something. And if it turns out to be a good idea, we'll tell you about it. If it's not, we might leave you some feedback that's not a good idea, but keep reading about it. And also tell us what you learn, enjoy, dislike about the paper that you read. And not just, I don't like this paper, period. We want to understand why, right? And review should be reasonable, short, but very concise. So you're not looking for filling up the space, but roughly it should be larger than half a page, about to a page maximum in like 10 pt font or something like that. Okay. Any questions about paper reviews? Okay. So some advice on reviewing. When doing reviews, be very critical. Always think about better ways of solving the problem than the authors propose or related problems. Do some background reading, not necessarily super careful, but make sure you understand what was the state of the art for the paper at the time when it was published. This is the best way of learning about research problem and the topic. Think about forming a literature survey or research proposals based on the paper for your future studies if you find it interesting. So how to submit? There's very few of us. There's no reason to have like some special stuff. So just email us to the special email, computersciencecourse2224arch@gmail.com. That will be on the website as well. It's due Thursday, 1 p.m. each week. So essentially we expect you to submit your review before the class, right? And next week, you're going to review this paper called Dark Silicon and the End of Multi-Core Scaling by Hadi Esmail Zadeh, that was published at ISCA 2011. Okay. So yeah, all the papers are available online. Yeah. So the research project is your chance to explore in-depth a computer architecture topic that interests you. Perhaps even publish your innovation in a top computer architecture systems or ML conference. Start thinking about your project and topic from now on. Interact with me, and I guess I had a typo. I had still an alt TA from last year, so talk to me or with Hossein. Use Piazza to discuss ideas, form teams based on your research interests, your research areas, or just personal preferences. Okay. So the major goal is to develop new insight, and what you're trying to do is solve a problem in a new way or elevate, analyze systems ideas. Okay, there's still some stuff to cover, but I prefer you guys to have some break from me talking and me drinking some water. So we'll take a short break right now. Let's say 10 minutes should be fine, right? And then we'll continue in 10 minutes. Any questions so far? Okay, then let's everyone have a 10-minute break, and I'll see you at 2:10. Okay, guys, let's continue. Okay, so we will finish in talking about the research project. As I said, the goal is to develop new insight. And there are usually two different types of projects that you might have in this class. Type 1 is you develop new ideas to solve an important problem. You rigorously evaluate the benefits and limitations of these ideas. Another possible type of papers, you perform some very rigorous analysis and understanding of existing systems or some previously proposed ideas that are not necessarily new, but you learn something new from them. And you may propose some new potential solutions based on the insights you learn. So it's either new ideas or new analysis type of papers. So both the problem and ideas needs to be very concrete so that you can actually achieve something within a few months. And problem and goals needs to be very clear. So for research proposals, what should you aim for to answer? What is the problem? Why is it hard? How is it solved today? What is the new technical ideas in this area? Why we can succeed now compared to previously, why people didn't solve this problem before? What is the impact if you're wildly successful? So what would be the impact to the industry, to academia, if you actually solve this problem? And I have a link here to George Hamel catechesis that would help you to learn more about how to write papers. So the questions I frequently ask, where do I get ideas? I'm just starting, I'm not sure where to look. To be honest, there's no shortcut. If you want to come up something on your own, other than given by someone, you'd have to read a lot of papers. Find areas you got interested in, focus on that problem from this area and keep reading in this area. As you look into that, you will start to find something. So that's one source. Another source is if you come to me and says, I'm in this area, is there anything interesting you have in mind? We might provide you some ideas for projects. So it might not necessarily perfectly align with what you do, but I might be good enough for you. A good way of finding topics to survey or to project on is examining the provided project ideas that we're going to talk about, read more papers, assign papers and other papers, look at follow-up work on the projects I'm going to talk in this class, and examining papers from the top computer architecture conferences, or systems conferences such as ISCR, Micro, HPC, ASPLOS, or MLSys. So this is the RAS milestone list. Project proposals, about 1 to 2 pages, not super long, but please be concrete. October 1st. By the way, going over the limit is fine. We're not going to be picky about that, but just make sure that it answers those key questions I listed before. Progress report, or like me project report, 2, 3, 4 pages, early November 5th. Poster presentation roughly December 3rd. So we'll figure out what the logistic for it and which days are available. So I cannot give you the exact date. Usually it's the last week of the class, right? The last lecture. And project report, 6 to 8 pages. Typically it can be longer depending on how many results you get. And we're aiming at December 10th. So some of these deadlines might slightly change, but if they change, they would be pushed a little bit back rather than early, right? So we won't hurt you. So we might move some deadline by a few days maximum. Any questions? So when that happens, there will be corresponding announcement. Okay. So those, so presentations. So what you're supposed to do. After the project topic is selected and you form a team, you need to identify the key related works, usually 1 to 3 papers. You can do more, but then you can cover them in depth, right? So it's better to be focused, 1 to 3 papers. Sign up for the day to present your related work. Your presentation should aim for 30 minutes without interruptions. With interruptions, practically, we've seen things going over an hour. So that's the reality. I will see how it's going to be with a virtual class, but usually we do ask, and I ask a lot of questions to this related work. So don't be surprised. The exact schedule of the talks will be posted as the project groups are formed. So what's going to happen, you're going to get a Google Doc or an Excel spreadsheet where shared file where you can enter your preference. We're going to give you some slots. Usually we had 2 slots per concrete day, and it's first come, first serve, right? So you pick a slot that fits your needs. Everything will be towards the second half of the class. Any questions? Okay. So what should you cover in the presentation? So the summary of the work, what is the key problem, key ideas and insights, detailed mechanism that the authors propose, but be reasonable, don't put all the low-level details, and the most interesting results. That's the summary part. Then talk about the strengths and the weaknesses. Remember, similarly to reviewing a paper, the detailed discussions on both sides. Okay, I got some questions. Let me have a look. Oops.
It wasn't actually a question. I was just commenting in the break.
Oh, okay, I see. Sorry, you just noticed. Okay, so then there's a discussion, future research directions, alternative ways of solving the problem, importance of the problem, anything interesting about the research direction. What did you like and what you did not like about that particular paper that you select? Remember, I strongly suggest you to pick the papers that are actually super relevant to your project, so that would help to write a related work sections of your final report, right? So this is why it's important to identify these keywords very early. Okay, so this is kind of finishes, I would say, all the logistics and also all their helpful content to, to understand you how to do reviews and how to do projects. So let's now talk about why computer architecture matters and why relevant and why it's worth taking this course. Okay, so the first 2 questions I want to pose for you and we'll want to think about together. What has made computing so important? So what is the backbone of computing industry? What makes us excited to work about it while most of the undergrads right now are willing to be CS majors? So there are several big things that make things possible, and programmability. So the ability to change things very rapidly and to add new, intellectual property easily. So one important thing about programmability is that you create IP without actual physical medium. So, a lot of countries like to pump oil, right, or gas. It gives you a lot of money, but you trade physical substance for money, right? And if you don't have it, then you kind of lose the income. So you produce something physical and it has its limit and cost. The thing about creating new intellectual property in this industry is that after you created a piece of software, every new copy is almost free, right? You don't really consume any physical medium. So that's a beauty, and that's why a lot of top companies right now, that you would see, changing the market right now are actually IT companies. Another important invention in this field is obviously networking. So people were able to connect individual computational units into massive arrays, clusters, networks that make computing really pervasive and affects all spheres of our life. Let's talk about how those 2 aspects were possible. So what really makes computers programmable? The first computers were actually like pieces of hardware, not particularly flexible. In fact, a lot of people for a long time thought that hardware matters. It's like big companies like IBM refused to understand the value of software, for example, for a long time. This is how they miss companies, like Microsoft, for example, right? They just thought software is nothing. So the big part of programmability is a von Neumann architecture for general purpose processes. It's a very simple, it has a very simple definition. It has 2 major components, or 3 major components, if you will. It has memory, random access memory. It has central processing unit that has, in the simplest case, it has control unit logic for control flow and arithmetic logic unit to perform computation. and it can take input and generate some output, right? So those are pretty much the building basic block. Memory stores program and data, both of it. Program instructions execute sequentially. This simple architecture was proposed in mid 50s and quickly becomes dominant due to its simplicity. Then people gets, things gets more complicated when people look for performance. So people start to add stages to this, pipeline, and we get all these different things like branch predictor fetches, encoders, decoders, register files, integer versus floating point units. We got caches at some point back in the 70s, and register file. So what's the trade-off here? Well, programmability, the more generic you want to go, the higher the probability is, but you pay a significant cost. Remember I said everything in this area is a trade-off. The more general purpose is my chip, the lower efficiency it has. It's pretty much fundamental because you will have to trade some silicon, some logic to implement that generality. If you keep going, do you guys see my mouse?
Yes.
Yeah,
we can.
I can see you.
Yeah, so you see if I keep going through this curves down, then at the bottom, like here, the first CMD units, that's a vectoral units. It's quite general and easy to program, and they give you high efficiency, but it's not as generic. Like not everything can be vectorized efficiently. If you keep going down, you get GPUs. If you keep going down here and you keep getting better efficiency, you can get FPGAs. At least that was the hope. And at the very bottom, there are ASICs. So the deeper I go, the higher the efficiency as defined by performance per dollar or performance per watt, right? But essentially, this is a trade-off here. What is a good trade-off here in each particular applications you define for yourself, but that's something that our area offers. Okay, I pose a question to you. Keep talking about computing industry. So what is the fundamental difference between the computing industry and the paper towel industry? So those are two industries, both has profit. So what's the fundamental difference between the two? Anyone wants to take on the question?
Well, me and Mustafa kind of know the answer.
Yeah.
This should be fine then, yeah. Okay, so I guess no volunteers and some people know the answer. So just by looking at it, like paper towel industry is not particularly changing, right? It's an industry of replacement. You consume some and you replace it, right? That's industry, like paper towel industry. To be honest, some industries are very similar to that. Like there are a lot of industries that don't really grow, don't innovate that much. Well, our area is an industry of new possibilities. Things keep changing, things become more and more radical, and every year something new and really interesting and new keep coming. So this is why it makes this area so exciting. So can we continue to be this? How can we continue to be this area of new possibilities? So new areas are always evolving, and we need to look for opportunities. I mean, I'm not gonna talk about the things that are the most popular right now, like ML, but beyond that, there is a personalized healthcare. Like, can we, instead of you getting a general purpose drugs, right, that might or might not work for you, can we use your DNA and identify the drug that works well for you? What the compute resources required to that? Right now, it's prohibitively expensive. There are a lot of challenges to that. How we can make this possible? Virtual reality, real-time translators. So all of those applications are very exciting, and they're not impossible, right? Okay. So how fundamentally, as a computer industry or IT industry, how we became an industry of new possibilities? What was the driving force of it? One of the biggest driving force was so-called Moore's law. I hope some of you remember that if you took an undergrad computer architecture class, but I remind you, so roughly every 2 years, for more than 50 years, we were able to double the number of transistors every 2 years, build high performance from those transistors. So general purpose processors that make transistors available to masses, and we're able to increase performance using twice more transistors, roughly 1.8x every 2 years, and lower the cost of computing 1.8x every 2 years. Remember, that was for a period over 50 years. It kind of tells you how good of an original idea of using computing design and using transistors was to begin with. It was very scalable. It has a huge room for improvement. So obviously every exponential law will come to an end. And so Moore's law also came to an end, but it drove our industry for more than 50 years. So what is the catch there? So, and what starts to break? So let me show you this graph that shows you essentially how the Moore's law over time came. So the Moore's law claimed that we can get more transistors, and up until recently, we were actually able to keep up with it. If you look at this graph starting in 1970, you see, that's an exponential curve. So linear curve for Moore's law here really means an exponential curve, right, on a proper plot. And you see we were able to keep increasing the transistor count, right? So for a long time, it was possible until somewhere around year 2006, 2007, something happened. And this was the power wall. So out of a sudden, we can still have all these transistors, but we cannot power them up without melting the chip, right? So this is what starts to limit us. So, and what is the really problem here is the first thing that broke before Moore's law broke. Some people will argue that the Moore's law is, still alive. I would argue that that's not true anymore in any meaningful definitions. You can see how Intel struggles right now with their, new 7nm chips, right? They cannot really tape out things with their, projected scalability, no matter how you define it. What was broken before Moore's law was broken is a so-called Dennard scaling, right? So by doubling the transistors before, we scaled them down, and the hope was to get the benefits in several different dimensions. So we reduced the area by half, capacitance by 0.7, and frequency can go up. So using these equations, we were able to roughly reduce the power half, and so that's where things were beneficial, right? That's why we can have smaller transistors with lower power all the time, and then we had more of them, so it kind of keep the power budget more or less constant, right, by having twice more transistors. Well, things starts to break. We are not able to supply the voltage part of it was broken, so the power supply is also broken, so we can't really scale with respect to power. So as power starts to go up, eventually the chip melted. It's an interesting anecdote there that I like to tell the students, that even though architects predicted and circuits people predicted it for a long time, the managers at Intel didn't want to accept this thing. So if you go and dig online, you will find their projections back in 2006, how Intel has the projection to build 5 gigahertz, 7 gigahertz, 8 gigahertz chips in 2009 and 2010. And they thought if they just push the engineers hard enough, those guys are going to deliver. Well, engineers were complaining the same problems are coming, but managers don't want to listen. They will keep having their slide acts with those projections. You know what? At the end of the day, engineers did what they were asked for. They generated chip, and surprise, surprise, it melted when they tried at 5 gigahertz, right? Like literally physically melted. So Intel has to rapidly, change all the projections in their, nearest futures, and then, the new thing happened, which is a multi-core error, which we're going to talk about. So out of a sudden, Intel still can't sell you more transistors and really willing to sell you more transistors, but they cannot put it on the single chip anymore. So now they started to convince you that having more cores is useful, which, as you can realize, it's not always the case for you. So one way to think about this problem, and you're going to read about that, is as a dark silicon. So if I can still have more transistors, but I can't power them all the time at a full capacity, I can think about something called dark silicon. So essentially, fraction of transistors might not be fully powered at all the times due to power constraints, and I can turn and off pieces of silicon depending on a concrete demands. So looking back at what happened, so this is how the chip looks like in 1971, below 1 megahertz, right? Just think about it. Like we are talking about, you know, multiple gigahertz right now. So by 2003, with this endless exponential scaling where people at Intel, I mean, some people at Intel, let's say, were believing that's going to be forever. It actually was over. So that's where Dennard scaling broke. And you know what, we cannot do these chips anymore. So right now, the best chips you see is like maybe 4 gigahertz maximum, still 20 years from then. And the so-called multi-core era started. So Intel started to sell you 2 cores, 4 cores, 8 cores, and more cores, right? And try to convince you that that's actually useful for you. So that happens for a while, but then that scaling also has its limits. But from the application perspective, it's not easy to benefit from multi-core stuff. Out of a sudden, everything becomes parallel, and it's not always beneficial for a single application. That's one problem. That's not the only problem that happened. Another problem was scaling issues related to memory and DRAM. So I've shown you the trend of compute over like 50 years. What happens with DRAM? Well, DRAM also has scalability changes. So without telling too much about DRAM right now, we're going to have a specific lecture about that. What is the interesting about it? So DRAM, in the easiest form you can think about, is just storage. It consists of multiple cells that can store 1 bit of information, 0, 1, somehow. And with technology scaling, we will keep making it smaller and smaller, similar to CPUs. And DRAM scaling enabled very high capacity at a very low cost. This is why we are now having tens of hundreds of gigabytes of memory in modern computers. But when I was in high school, I was dreaming to have a machine with 16 megabyte of DRAM. And that was considered to be the state-of-the-art machine back then. So it was scaling, like in my lifetime, it scaled like by 4 orders of magnitude. So let's look at this trend. So on the bottom, we had start of the mass production of DRAM in 80s. On the y-axis, we had megabits per chip, right? So you can see that graph is also exponential, right, in scale. So log scale. So if you look here, you're going to see that this linear curves pretty much tells you that every 2 years, we can give you the capacity needed in just 1.5 years. So we can double in 1.5 years. That align nicely with the compute demands. So compute was improving by almost 2x every 2 years, and capacity was keep going up. That's why this trend was continuing. So that's capacity. But then this trend starts to slow down, and then it becomes more like 2x every 3 years. So DRAM scaling was starting to get difficult. That's the capacity challenge. Another problem is that as you make it smaller and smaller, you'll get to physical laws eventually, where quantum effects make the bit flips. So manufacturing reliable DRAM cells that don't affect each other is getting more and more difficult. And there is some traditional approach to that, where just forcing you to make DRAM more reliable, which becomes impractical. And so you need to try out and come up with some new and creative ways to do it. So DRAM has strict reliability guarantees right now, which might change in the new approach where you change this guarantee over time. Okay, so this is some interesting stuff you can do if you want to optimize DRAM. And for that to happen, like one thing you need to do is to break the abstraction. So essentially, if you're just going to stay at one level and looking at the DRAM as a monolithic piece, you can't really change that abstraction. So the way to deal is essentially to look at that abstraction level from the problem to the circuits, remember? And essentially the goal is to potentially revise the interaction between the main memory and the operating systems, and maybe shift some of these reliability issues to the operating system itself. So this is type of research, people do in computer architecture field. Okay, so that was just one example of what kind of topics you might be interested in this field, is trying to deal with DRAM scalability issues. We're going to have a separate lecture in DRAM. In the interest of time, I'm not going to go too deeply into that. What I really finished this class with is to give you a general advice on doing research, right? That's the plan right now. Any questions so far? Okay.
Sorry, I just had a
question. Go ahead.
question. So do you not foresee any like radical hardware changes in the next maybe 10 years then? So I guess hardware performance is kind of dying.
Very good question. Yeah, I'll tell you my opinion. Like, it's hard to predict the future unless you really shape it yourself, which some people try to do. So, so several years ago, I think around 2018, no, actually around 2016, at the end of Obama administration in US, they create a special summit and introduce all the top architects in the field. And the government in US tried to learn what the future is like, so what to expect. So that meeting that brought all the top architects in our field, they come up with some summary on the conclusions from this meeting. And the not so good news for their near future was that, it was clear that we don't have any foreseeable replacement for the CMOS technology. So there is no easy way to go to somewhere else. There's no technology in the foreseeable future that can be mass produced in right quantities and right scalability that can replace CMOS-based technology. So the conclusion was, for the next 5 to 10 years, for sure, neither of the existing promising technologies like quantum won't be able to replace anything. So we stuck with it. To make things worse, it's not going to scale anymore because we reach the fundamental limits of scalability. So the only way to move forward is be creative. So for 50 years, we were moving the field forward by just cramming more transistors in the same area and keeping the budget more or less the same. And free lunch is over. Like, you scale it down to as much as you can. So the only way to scale things further is to be more creative. So that's more or less conclusion from it. It's been 4 years ago. I don't think much changed since then. Everything else, all other technologies right now you can think about, bio, quantum, is still a tiny prototype and by no means can be mass produced in any foreseeable future. Even if they can only cover some very unique domains. Okay.
So I guess by creative, you mean like creative with the software?
You need to be creative across the whole stack. So it's like if you use approximate computing, for example, you can win a lot, but you need to involve application level. You cannot just do change at the hardware level alone, right? Okay. Sorry guys,
Yeah.
I need to... My keyboard was losing power. Okay, any other questions?
Again, I have a question.
Yeah.
Back in the beginning, you said there's a von Neumann model of execution, right?
Yeah.
And you said it became dominant. Now with a new technology, is anybody challenging the von Neumann model, or we're sticking with it? Are there any more like newer proposals for a more efficient one, perhaps?
Yeah, we already violated it. So it's like von Neumann model was violated. The most first serious violation was in 90s. It's like as soon as you start being out of order, that's not von Neumann model anymore. So like von Neumann model was just done by mathematicians, was very sequential. It was not really thinking about performance. At some point, like it was very easy model to reason is. It's amazing because everything has an order, timestamps a fix, everything is amazing. Well, at some point, the performance forces us to make things parallel, and a lot of things that model promised was breaking. So you had to go and use theories from like Lamport clock and everything that was invented in distributed systems to move things forward. But essentially, it's already broken, but it helped to build the shape of the thing, and this central processing unit, LUs, memory, and all this structure still alive to these days, right? But certain pieces of it already violated. It's like a classical physics. You just Newton physics up until it breaks somewhere, and then you make a patch for it. It doesn't mean that Newton was completely wrong. It just was, you know, approximately correct to that level in those dimensions. When you go to a new area, then the thing starts to break.
Okay, thank you.
Any other questions, guys?
Do you think that, I see the graphics processing industry seems to be moving towards including a lot of other very specialized things on their chips? Do you think this is sort of a symptom of that?
Yeah, so essentially there's that good question that we got before about what we can do. I think Andrew asked it about where we want to go with existing technology. Part of that is one proposal was hardware acceleration. Essentially, it's not just graphics. Graphics is just one early example where it was critical to do hardware acceleration. So essentially sacrificing generality to get performance. So right now we're in the area where essentially all main breakthrough in computer architecture happens not on general purpose end, but mostly on the accelerator end. Machine learning, you know, security, cryptography, this is all accelerated chips. You see how crazy this industry right now is about building machine learning hardware, for example, right? They're going to do this for a few years until there's going to be yet another super strong applications, and everyone's going to build chips for that. So I think the foreseeable future is figuring out how to build those accelerators generically enough so you don't cover just one use case, but more. So why, say, NVIDIA was so successful, right? They built something that would aim for graphics, but it turns out the idea is good enough for other use cases. High performance computing, machine learning, it turns out that it can be done using the same basic idea. So that make those chips reasonably good and a good fit, and you know, company get lucky. Essentially, the company got lucky in some sense, right? They didn't plan for being useful for ML; they just take on the opportunity, right? So I think that the big, so essentially, it's not just graphics; it's essentially each domain that would require more compute than what you can get with general purpose would have to build accelerators. So people already inject those programmable accelerators. So Azure and AWS offered you FPGA instances right now in the cloud. So you don't need to own it. You can just ship your code to do it. But the problem is FPGAs, good luck programming them, right? They're the programming interface. You either, if you want to get performance, you program with Verilog, and then debugging and engineering time is humongous. Or you can use high performance, high level synthesis, but then good luck getting performance from that. Yeah. So this is where the problems are, right? Like people want to use accelerators, the problem how to program them well. There are tons of theoretical papers from all top schools on that. I don't think anyone even solved 10% of the problem in that space. And the compute demands are keep growing. You've seen, if you follow the ML field, you've seen the blog post from OpenAI, and then it's showing how much costs for training these new big models cost. It's like, you know, to train a single model, sometimes it's as expensive as to own like 5 cars in your lifetime, right? In terms of carbon footprint and the cost. So those models are humongous. We also generate a lot of data. So it puts a huge demand on compute, on processing that compute, right? Okay, any other questions? Okay, let's talk in a more generic term about how we try to advance research and development. And I will try to give you those feedback on how to avoid some common mistakes people do in their research in the grad school. So the first thing is we are trying to learn by example, learning by doing, and learning by being open and having critical discussions. So learning by examples mean reading and evaluating strong and seminal papers in your area. So that why, like usually the grad school starts with masters, right? You need to become a master of a particular area, right? So that means you're not necessarily contributing to the new things yet, but you already very well understand how the state art looks. And for that, you need to understand what's the best in that narrow area is. You're learning by doing, so semester-long research project and online discussions and discussions on Piazza and paper reviews. Okay, so let's go to fundamentals. So what really is the goal of research, other than, you know, some people can say just earn money, but like fundamentally, what is their, you know, really the goal of research? The goal is to generate new insight, right? So that insights can enable something that previously didn't exist before, like, you know, machine translation on your cell phone, right? Like you can talk and your text will be, you know, transformed in your voice will be transformed into text, and then it will do a search, right, and generate you some, you know, results. That was not possible 10 years ago. In fact, if you would talk to the most excited people in ML, they would think it's even invisible for the next 20 years. They thought it's way long thing to go. Well, until, you know, several breakthrough happens, and then out of a sudden it was possible. Research in the engineering field is always a hunt for those insights that can eventually impact the world. So the basic advice from me and from some other researchers, to be honest, is you need to choose great problems to solve, and you need to get a good taste to the problem. There is an infinite number of different problems to solve that are difficult, important, and have high impact, but you need to have a good taste on what's promising right now that are nearly the breakthrough and that can change the world significantly. It's hard to do it in isolation. The times of those geniuses, I believe, are done. So you really need to understand what others are doing. So read heavily and critically, think big and out of the box, question the common wisdom, and don't restrain yourself to tweaks. This latter comment is extremely strong about the industry. So industry is driven by profit. The profit means quick deadline, shipping product quickly, and that forces the engineers to not think about fundamental things and restrain themselves to small fixes and tweaks between each iteration. And that it ended up generating product that consists of just gazillions of tweaks. So the reasons why you are hopefully here in the grad school for most of you is because you want to look for more fundamental, more radical ideas and don't restrain yourself to tweaks. Another important thing is aim high, and the amount of knowledge generated right now is humongous. It's not okay to come up with a great idea and publish it. You need to write and present it really well. Like some of you might have seen that in, say, machine learning alone, on arXiv, there are more than 100 papers published each day, right? It's unsustainable to read and control what's generated and make sure that you understand it well. So you want this special paper, and there are many dimensions on how you can make this special paper, is that people want to read and would care about. And that's how you can get both recognition and how you can gonna make an impact, right? So what is the typical problem that the students have in their research? Well, you have this dark street and there is a light there. That's what the people know right now. And well, if you lost the keys there and you're looking for something, the most convenient place to search is under the light, right? So that's what you're going to search for. Well, what if the keys are there, right? So the most convenient place is not the best one. So don't restrain yourself to search where it's the most convenient because of your skill set, because of what's known right now. Don't artificially limit yourself. You can achieve way more if you don't, we're going to put constraint on yourself. Another problem that is true for many computer architects, but for systems in other areas as well. So whenever they do some planning, they aim there and they think that that's what they're going to be 5-10 years from now. That never happens. You always need to aim higher to enable this point. Why this is important? So what very frequently happens, if I ask someone, like my student, you're proposing a new idea. If you're widely successful with your idea, how much of an impact it's going to say? If your students come and says, well, if that works, this works, and works, that works, and I can speed up my processor by 10%, you know what? By the time you go and implement this in reality, it's not going to be 10% faster. It's going to be 5% worse. So that's going to be a waste. Don't start with something that is that small and incremental from the beginning. So then you're going to be disappointed at the end. You're going to fight for the single-digit percentages. This is why I was interested in the core computer architecture when I was an undergrad, 20 years ago. But right now, I would say that that's not something I'm going to spend my time on. I'm not interested in doing, say, research and branch predictions, right? Because that, to my opinion, is more or less like a solved area. There's very little I can contribute there. So I'm looking at the topics where I see way more potential, and I look for topics where I can, speed up things by 10x. And then if I actually go and implement, maybe 10x will become 5x, but it's still something to people that care about. So there's a very simple research formula that you want to think about investing in your time in research. To be honest, at this point of time, your most valuable asset is your time, right? So you want to think about what's the best research of investment for your time. At the top, we have reward. At the bottom, we have risk multiplied by effort, right? So you want to maximize your reward by minimizing your risk and minimizing your effort. It looks trivial, but it's not that trivial. And you need to apply this formula every time you decide to go into some research topic. So first of all, reward. How would you need to think about it? You always should think about not let me figure out what the reward will be when I implement these things. No, never do this. Try to guess under reasonable constraint, if I'm wildly successful with this idea, what a difference it's going to make in my field and to the society in general. So what is the possible reward I can get, and try to re-estimate it every time you keep doing your research. How about the effort? So the goal about the effort, and that's a big difference from industry, guys, remember that. Learn as much as possible with as little work as possible. That's not about being lazy. It's just that there is, again, an infinite possibilities in experiments you can run. Just running tons of experiments with little impact is not going to help anyone. You're going to write scripts to run them, then you're going to run, you analyze them, and there's not a lot to learn. Think strategically about which experiment is going to allow you to learn and to generate more insight, and do those as minimal as possible. You need to be very smart about that. In fact, good graduate students, that they have a huge advantage over industry, because industry is spoiled by tons of hardware available to them to run experiments. So they do a lot of rubbish, useless stuff. Graduate students usually tend to be more limited with their resources. They're way more creative about that. So this is where a lot of great ideas are coming from academia versus industry. In terms of effort, another important aspect, do the minimal analysis and experimentation necessary to make your point. So try not to run useless experiments. Do experiments to make your point. So always remember that research is a hunt for insight. You need to go off the beaten path to find your insights. You cannot just stay and just follow and conform with existing rules. So I recommend this talk by Bill Daly, who is right now, he's a professor at Stanford, and he's also, I think he's senior vice president at NVIDIA, and also he oversees the whole research at NVIDIA right now. So like 10 years ago, he gave a nice talk about moving the needle, effective computer architecture research in academia and industry. And the past few slides that I present about the search for insights were from Bill Daly's talk. So things to remember from you is when you're a computer architect, what really transfers from academia or R&D in industry is insight, not your academic designs, not your performance numbers. Nobody cares about that. It's just to make your point. That's what the value is. So sometimes students think that their numbers is what they make their paper valuable. No, your insights and what you learn, that would make your paper valuable and your thesis valuable. And more good advice from some, wise man is the purpose of computing is insight, not numbers. This is from Richard Hanning, right? So insight, that's what you're looking at. That's why you're in grad school, remember? And that's pretty much it for today. I think I'm 5 minutes early than what I planned, so I'm happy to take your questions. These guys, don't be shy. Was everything clear about what you need to do in this class? I hope the production logistics was clear. I hope you made my point on how I believe research needs to be done. By the way, if you're gonna talk to someone from a different field, especially from a more theoretical field, they may have a different opinion on what I said, right? But this is from my years of experience on how to make impact on the world. right? A lot of things I learned, look, when I was a junior grad student, when I arrived for my PhD at Carnegie Mellon University, I thought if I publish really good papers, that's it, the job is done. Well, I learned a lot after that is that like most people don't care about the papers you published, right? It's your job then to publish it first, make your community accept it. So there is a check mark on it as being pre-approved. And then you have to go and prove the industry that what you did is actually valuable. And they're not lazy. They're just too much information. They're too busy. So it's your job to advertise it through social media from, back then it was possible to travel. So you actually have to travel and, give talks, make sure people know about your work. That's how you make impact. I know some of the things I said today might look like trivial and obvious, but believe me, it's, it's not for some people as obvious, especially as a grad student. There's always tendency to dive into too low-level technical details and only care about the numbers you generate at the end because you feel like that's what you produce right at the end in systems. Remember, this is not. You are given these numbers to confirm your logic and your point and your insight, right? So it's insight that transfers. That's a technological transfer. Okay. Any other questions, guys? Any suggestions? Was I too fast today or too slow? Mustafa, we can hear you. I think you're trying to talk.
Yeah, we didn't really cover any significant material. Like it was more of a high-level overview. So there's I don't have any questions from that.
Yeah, I don't want to.
A lot of it was clear.
That,
Yeah.
I don't want to scare people in the first lecture. Like, that's what I do in my undergrad class, but not in grad.
This is B58, right? You start talking about physics.
Yeah. And B58, I talk about, PN junctions,
That's the scariest part of the course.
Yeah. That's fine. It's like you need brave people here. Here, people are already brave enough to join grad school, so you don't need to scare them any further. They're already scared. Okay. Any questions from anyone? So the main thing right now to you, go to Piazza, look for partners, right? So some people that belongs to the same research group, it might be easier for you to form, teams. But it's also harder because both of you might have a bias on which topic you want to work and it might mismatch. So I actually found that not always my students are willing to work, together on the same project because both wants to be the driver of a particular topic, right? So anyway, explore your options. The best way is to make a post on Piazza saying, I'm this and this, that's my name, this is my skill set, and this is roughly the areas I want to do the project on. Any other questions? Okay, if there are no questions, that I guess I'm glad, we started with 17 people, we still have 17 people here. That's much better than with most undergrad classes. So I treated
I think the real test is how many people show up next week.
It's true. But even it was like in the undergrad class, it's important, the numbers keep changing the whole 2 hours. They keep, people keep jumping and leaving and things like that. It's quite sporadic, I had to say. Yeah, so here it's more stable. Okay, I think then we are done for today. Thank everyone. If you don't have any questions, then there is something. Yes, so the question is, well, lecture is recorded. Yes, everything is recorded. So it's going to happen after the lecture is done. Then, it's going to take another 30 minutes when the Zoom is going to save it on my, machine. And after that, we're going to post it. So in a day or two, you're going to get the files available for you. And the slides are already out. Yeah, so everything will be recorded. That's one of the advantages of the pandemic. So everything is now recorded. No disadvantages, yeah. Okay, thank you, guys.
Thank you.
All right, bye-bye, thank you.
Bye.
Bye.